But you can call this a gas, that one. This is a one chamber. Or volume of a gas between a layer. So what thermodynamic process it will undergo? So Newton assumed that Sir Isaac Newton, he assumed that the air or a gas here, air or a gas undergo a isothermal process. Yeah, just assume that one. That particular thing will undergo an isothermal process. No, because of isothermal process. So what is the pressure? No. So when sound wave propagates, I think okay, I'll write complete description again. When sound wave propagates, the air or gas undergo isothermal process. This is what I assumed. So isothermal process, now I think we are quite familiar. PV equal to constant. Then I'll differentiate PdV plus VdP equal to 0. So therefore, in place of dP, what we can write it as? Because I wanted to replace bulk modulus. So dP is equal to, I can write it as P by dV by V. We know bulk modulus is equal to P, no, it should be, sorry. P is equal to, we'll agree this, the above equation. And other side, we know bulk modulus equal to dP by dV by V. So what Newton assumed is like the equation was this much, no? So you place in place of B as the pressure. What is P? P is a mean atmospheric pressure. What is rho? Mean atmospheric density. That's what he assumed that one. And he substituted the value. What is the P naught? I think 101 kilopascal, 10 to the power of 5 Newton per meter square. Mean atmospheric density, how much it is, like 1 kg per meter, 1.01 kg per meter cube. When he substituted, he got the speed of sound something around 320 or something. But practically what he measured, no, so like a 280 something he got it. Practically what happened, it was 340. He was unable to further conclude anything. So he just left it here. So later on what happened, the later on Laplace what happened. So Sir Laplace, okay, Laplace correction. So another scientist by name called Laplace, what he assumed that when sound wave propagates, the air gas undergo adiabatic process is what he said. The reason for that, because the compression rarefaction, they will undergo so rapidly that the air will not get any time to exchange heat. But what Sir Newton assumed is like when the compression rarefaction occurs, what happens? They will occur gradually so that the air will get sufficient time to exchange heat from the surrounding. If the exchange heat means definitely what happened, and the temperature of gas remains constant, he assumed it. And because of that, what happened? He assumed it to be isothermal process. But what Laplace he assumed is like the compression rarefaction occurs so rapidly because compression rarefaction. So it occurs so rapidly that the air will not get sufficient time to exchange heat. So therefore, it will undergo adiabatic process. The compression rarefaction occurs rapidly so that the gas or air will not get sufficient time to exchange heat with the surroundings. So here what Newton assumed is like the compression rarefaction occurs gradually so that the air will get sufficient time to exchange it. That's why he made it as isothermal process. Rapidly occurs rapidly. This is very important. For according to Newton what happened, it will occur gradually. Oh, we have to add no because they will ask you these things as a conceptual question. No? Let me we'll take this sentence. Better let me write the compression rarefaction occurs slowly and gas will enough time to exchange heat so temperature of gas now you do have good number of conceptual questions where they will ask you this data. That's why I just this is what the assumption of the Newton regarding its sound wave propagation. Okay, fine. So when he practically did know, there was some error. And what Laplace was able to assume this one. He just made a correction. It's not that Newton is wrong. So don't say like that. Correction. That's why we say Laplace correction. Different. So then when if the adiabatic process means what shall I do? PV to the power of gamma equal to constant I should put it. So then I'll replace the things. We'll see what will get it. There's a conceptual reason like this is what this one. So now we'll go for the derivation part. PV gamma equal, I think we know this P equal to gamma P is it okay directly because it mean in thermodynamics we have come across so gamma P is equal to not gamma rho, it is gamma P, and from bulk modulus comparing these two, so the equation for sound wave is this one, no? The speed of sound wave was B by rho. Therefore, what shall I write? B equal to gamma P. Now I'll replace it. Now you tell me what is gamma. It is called as Laplace correction, or you are quite familiar, no? It is also called as adiabatic exponent of gas, Cp by Cv of a gas. Okay, got the idea. So now we know PV equal to nRT. P, volume of a gas. So this will become V. Mass of a gas will be M by molecular mass RT. Or further, different forms. We'll try to see what all different forms. So this will become rho RT, that one. So P by rho, in place of P by rho, what I can write? RT by M naught. So this expression for speed of wave, one more form is gamma RT by M naught. For a given gas, what happened to gamma R by M naught? Gamma R by M naught will be a constant. So can we take that everything? So this will be, what is T? T is absolute temperature. So shall we write it in terms of 273 plus theta? This will be a better way, no? Theta is what? Temperature in degrees Celsius. Capital T is not time period, absolute temperature. Or temperature in Kelvin. Okay, now for a given gas, speed of the gas at 0 degrees Celsius. So how much it should be equal to? Gamma R by M naught 273. Speed of gas at any temperature. At speed of gas, speed of sound wave, sorry. Speed of sound wave at 0 degrees Celsius. Next, again, speed of sound wave at theta degrees Celsius. And this should be equal to how much? Gamma R M naught theta plus 270. Let me divide these two. V theta by V0. This should be equal to okay, theta, this will be 273 plus theta. I think I can further simplify V theta. This is equal to V naught. Theta means temperature here. So this should be equal to 1 plus theta by 273 to the power of 1 by 2. Further, 546. I think very good, no? This is, you need not to bother gamma M naught of a given gas. If you know speed of a sound in a given medium at 0 degrees Celsius, you can find out speed of sound in that medium at any temperature. What is theta? Just you substitute the temperature. This is applicable because we did binomial expansion. Theta temperature at 500 degrees Celsius. No, don't do that. It should be few tenths because binomial expansion is what we did, no? Theta very small. Very small means few tenths. 0 degrees Celsius. At 500 degrees Celsius, okay, don't use this formula. Better go for the accurate one. This is few tenths. If the temperature changes by few tenths, as you can compare. Speed of sound wave at 0 degrees Celsius in a gas. Okay, got this one. So like this, what happened? We are able to predict the speed of sound at any temperature T. So what is the speed of sound at any temperature T? Now, sir, this is about the gases only. But if the same sound wave propagates in a liquid, this is for gases. So for liquid solids, what we do? So let me just generalize. Speed of sound, this is a medium. For gases, what are the formulas? What is the formula? Gamma RT by M naught. For solids, it will become, the bulk modulus will become Y and it will be rho, where Y is Young's modulus. For liquids, the formula will be, so what is Y? What is gamma? Gamma equal to Cp by Cv. What is Y? What is Y? Young's modulus of solid. What is B? Bulk modulus of a liquid. Okay, for different mediums, the speed of the sound what happen can be arranged like this. So the sound wave propagates in a solid. Okay, then what is the Young's modulus of the solid you measure, and rho is the density of the solid. Substitute that, you will get the required thing. Okay, like this we are able to know. So as a sound wave propagates in a medium, so first of all, what all things like it? When a sound wave propagates in a medium, there'll be the layers will exude SHM about their mean portion. There's the one thing. I'll summarize. Let me summarize so that you'll be. This is the most important part of discussion. Yeah. Almost we can work out many numericals with this information. So when a sound wave propagates through a medium, the layers of a medium will exude SHM about their respective mean portion, and that is given by displacement wave. And what is a called as displacement amplitude? Okay, got this? Similarly, when a wave propagates through a medium, the pressure of a medium will vary. The different points of a medium will have excess pressure that is given by this pressure wave equation. Get this one? Then next again, density wave. So even the density of medium, the different points, the density. Tell me among all three, which will be easy to measure? I'm leaving it to student. You must answer. Can you measure displacement of layer? Anybody? Possible? Do we have instrument which will measure the displacement of a layer? Not possible, no. What is a layer, first of all? Here, say on paper, I'm drawing. I'm speaking in a room. Tell me what is the layer there? What is the layer? Here on paper, I'm showing vertical lines. Okay, fine, good. In a room, what is the layer? You have to break up your room. Suppose the distance between these two persons, you break up that as a cylinder. You break up that into equal parts, that will become a chamber. In each chamber, again, you can assume n number of layers. Pressure, no, layer is not a pressure. Layer is a medium. Layer is a medium, that one. Okay, this one. So here better, what is a layer? Each coil is a layer. Okay, got the idea? In this spring, each turn is a one layer. Like that, I can assume n number of layers, no? So can we now have an instrument which will detect the displacement of this turn? Is it possible? Say, I'll push and release. The person who holds one end of the spring and gently pushes towards right once, and he'll come back here. Then he will not move his arm. The arm is at rest. So it is at rest here now. Then what happened? The disturbance will propagate. So what is layer? Layer is one turn. Here. What is a chamber? Some group of turns. This is one chamber. Are you getting the idea? This one. So like that will happen. Is it possible to have an instrument which will predict the layer? No, not possible. Is it possible to measure the density? No, pressure will be easier. Oh, you mean to say pressure? Huh? Okay, fine. Yeah. The density, can you measure density? Very difficult. Yesterday only I was seeing, no, to measure density, how much we struggle. Measuring the variation of density is still more headache. Okay, these two are very difficult to measure. The easier one is the pressure variation. So therefore our priority will be now to focus more on pressure wave. So therefore what is capital A, will give some name for it. What is A? A is called as displacement amplitude. This is called as, these are very popularly, if you want to write del d rho m also. So I just wanted in the end, I'm just bringing that one. So pressure wave, displacement wave, pressure wave, and the density wave. Okay, like this of all, the pressure will be very easy for us to construct an instrument based on this pressure wave equation. So therefore the pressure of a medium will vary. The excess pressure, I can measure it. So therefore all our instruments will be based on this one. The ear, we have a diaphragm. All of you know the diaphragm. The diaphragm will respond for this pressure wave, not for these two. Different. So what all we have, mic, no? So the now I'm wearing the mic. The mic will respond for pressure wave. So all the instruments, what all we have, no, detectors of sound, they'll respond for pressure wave. Any doubt you have, you can clarify, because so much of imagination is what I'm trying to make you. Any doubt you have, you can really ask me now. I'll wait. Unmute, and you can talk with me. General displacement equation. Again, the Newton, what happened, we have like the wave propagation, the transverse wave propagation, same thing. At t equals 0, I see the displacement here. When it would have been generated, prior to that, t minus x by v. From there only it's brought it. See, at time t, if I see the disturbance here, when it would have been generated, prior to that, t minus x by v, because the disturbance will take some time to propagate. How we had a rope one, no, the same thing here. So I'm speaking now. When you are going to hear it, after some time, if I say hello, this hello output will propagate, no? After some time it will be available somewhere. So from there I brought it, traveling wave. At time t, the disturbance is here. When it would have been generated, t minus x by v. This was the equation. Any doubt, you can unmute and you can clarify your doubt. Because this is the background. Once you know this, rest all we can manage very easily, this total chapter. I'll write this one. Okay, no. Any doubt? Okay, fine. I'll. Okay, all of you. I think I tried my level best to make you imagination. Okay, please. You also try to see the animations, what all possible animations, get that idea. Then immediately start working numericals based on the speed of sound, all this particular thing. Now they may ask you a question: what is the uh, displacement of a layer at a position at a given time? I think it's just mathematics. No, use this equation. If they ask you what is the pressure at a given point at a given time, excess pressure, then what is the pressure? P naught plus delta P. So when a sound wave propagates, what when we are in a better position now, we can tell what is the pressure there, what is the density, that layer in what direction it is moving, what is the speed, all the things we can predict. Hope all of you, I tried my level best to impart this sound wave propagation. This is considered one of the most difficult for a teacher also to explain. This one. So with what all possible